Alright, so it says find the values of x and y that maximize and minimize the function p if p equals to x plus 3y. So what we're going to do is draw in our constraints and then look for a feasible region. So let's draw in our constraints. So we'll plot the point -3. And then use our slope of up 3 over 2. The line in this case will be solid. And then we will plot our additional point at +7. And then a slope of -1. This line is also solid. And then what I like to do at this point is do my shading. So the first line was y greater than or equal to. So our line would have been shaded above. And then our second line is y less than. So that tells me that we shaded below. And then our last two constraints are the x and y axis. So what that means is that this graph is bounded by the x and y axis. So it's also bounded along this line and this line. So we have to shade above and below those two lines. So our shaded region becomes enclosed by the two linear functions as well as the x and y axis. So what we have to do is find the points at which these lines or graphs all intersect. So the first and easiest point of intersection is the origin, or 0, 0. And if we plug 0 into both of those functions, we get 0. The next point of intersection I see is right here at about x equals 2. So again, in order to make sure like my graph was perfect, I would go back through and kind of look at my slopes and say, okay, that was supposed to go up 3 over 2. So that point is 2, 0. So we get 4. And then the next point is the point at which the two graphs intersect each other. And they intersect each other at 4, 3. So we get 17. And the last last point of intersection is here on the y-axis at the y-intercept of that second equation, which is 0, 7. So it says find the values of x and y's that maximize and minimize. So our maximized occurs at 0, 7, and the minimized occurs at 0, 0. So again, this function up here, P, that's called our objective function. These are called our constraints. The feasible region is our dark shaded region on the graph where our solutions come from, and our min and max values come from that objective function. Okay, so then we have a furniture manufacturer can make 30 to 60 tables a day and 40 to 100 chairs a day. It can make at most 120 units in one day. The profit on a table is 150 and the profit on a chair is 65. How many tables and chairs should they make to maximize their profit? What is their maximum profit? So again, let's talk about tables and chairs. So let's say that X is tables. And Y is chairs. That means constraint Y, X has to be between 30 and 60. And Y has to be between 40 and 100. And you can make at most 120 in one day. So that means that X plus Y has to be less than or equal to 120. The objective function will be your profit function. So that's your P of X, Y. And you make 150 on a table, so that would be like 150x. And you make 65 on a chair, so that would be 65y. So let's graph our constraints. So you can see here is I have on my axes already the green and blue lines representing the tables and chairs. So again, chairs is between 30 and 60. And you have 40 to 100. So we have this shaded region in here, which represents the number of units you can produce of tables and chairs. Now we have to determine what the number of units we can produce in one day are. So we're going to plot our x plus y less than or equal to 120. So that will go in your corner here. Because if you think about x plus y less than or equal to 120, x equaling 120 and y equaling 120 would represent my x and y intercepts. If you moved over your slope, it would be -1. So there's the line that represents the total number of units that you can produce per day. And then that constraint with the constraints on the number of tables and chairs would create this trapezoidal region in here. That represents all of the feasible possible solutions. Now the vertices are always going to be my min or max possible solutions. This asks me to graph and label the vertices. So I have a vertice at 30, 40. We have a point at 60, 40. We have a point at 30, 90. And a final point at 60, 60. Evaluate the profit at each vertex. So what we want to do is plug each of those points into our profit function. And determine which one will maximize our profit. Because as a company, you want to find your max profit. You want to know what will allow you to earn the most money. So if you plug in 30, 40, you would get $7,010 or 7,100, sorry. And then if you plug in your next point of 60, 40, we would assume if we're making more tables in a day that I'm going to make more money, which you do. So you have 11,600. If you plug in 3090, we're now producing more chairs and fewer tables. And you would make 10,350. And then if you made an equal number of tables and chairs, you would have 12,900. So again, we'll notice that max profit occurs when I make an even number of tables and chairs. Now, we know that that's not logical. You can't sell the same number of tables as you do chairs because every table needs more than one chair. So more than likely, the company's profit would probably be closer to this function here, where you make about 3 times as more chairs than tables, simply because we need to have more chairs than tables when setting up a set of tables and chairs. However, for the purpose of the problem, the answer is 60, 60. So it says the furniture manufacturing company can maximize profit by making 60 tables and 60 chairs. The maximum profit is $12,000 $900. Suppose the profit margin increases, so the profit on a table is $175. So this is a new objective function. And the profit on its share is 100. How much does that change our maximum profit? So you plug in your 60/60, but now we make $25 more per table and $35 more per share. And our profit increases to $16,500. So sometimes when you notice an item that used to sell for a certain amount of money sells for more money, this is why the company is looking to increase their profit, and they do that by raising their prices. Suppose you are selling cases of mixed nuts and roasted peanuts. You can order no more than a total of 500 cans and packages. You can spend no more than $600. How can you maximize your profit? How much is your max profit? Write your constraints. So our total order can be 500 cans and packages. But then we have to look over here at how many cans you get per case, what price you can sell the cans at, so where your profit is per case. For peanuts, it's packages, your payment per case, your profit per package, or your profit per case. So what you have to do is determine, okay, we're looking at cans and packages. So if X represents the number of cans, and Y represents the number of packages, where cans goes with the mixed nuts and packages goes with peanuts. I know that X plus Y has to be less than or equal to 500. And then I also know that I can't order a negative number of cans or packages, because we know that we have to have a positive number of cans and packages. So over here we'll label cans and packages. So I know I'm bounded by my X and Y axis. I know that my minimum and maximums are going to be at 500. So to utilize the whole graph, since this goes out to 10, I could go by 50s. So it'd be like 50, 100, 150, 200, 250, 300, 350, 400, 450, 500. So again, I know that I cannot purchase more then 500 of each, because that is my min or max. So I can connect my two x and y intercepts. And know that I'm going to shade below that region. So now comes the trickier part. So it says that 12 cans come per case. So when I purchase these items, I'm purchasing them as individual cans and packages. But I'm selling them as cases. And I'm trying to maximize my profit. So my profit is the x and y. However, my x and y kind of have a constraint on them because I make a profit of $18 per case of mixed nuts, but there's 12 cans in each case. So my x kind of has to take into account that idea of 12, right? So when I think about these in terms of cases, then I have to take into account where that 12 is really going to fall into play. So it's 12x and then it's 20y in terms of my profits to get me to my number of cases or packages per case. So if I pay $15 per case and there are 20 packages in a case, I have to take that into account when I look at my vertices. So my vertices are at 0, 0, 0, 500, and 500, 0. And then my profit is 18x plus 15y, where when I look at my x and y, I'm going to divide each of those numbers by that 12 and 20 to get them more logical. So if I sell no cans or no packages, how much money will I make? Nothing. If I sell only roasted peanuts or only cans, so sorry, that should be divided by your 20, not multiplied by 20. And if I buy only cans and no peanuts, we would make a profit of $375. And if I sold only mixed nuts and no peanuts, we would make a profit of $750. So we would want to sell mixed nuts over roasted peanuts. Okay, so that kind of summarizes the unit on linear programming. So there are a few more problems for you on those next couple pages. So we did 8 to 13 yesterday. We are picking up with the next page in that unit today. So you are picking up with 14. I believe you go through 17. And then you have 2 word problems at 23 and 24. So again, you're looking at those next pages in the linear programming homework, and you're doing 14 to 17 and 23 to 24. All of those need uploaded by 7:35 tomorrow morning. So those are uploaded and due at 7:35 tomorrow morning. I'll be going over all of these on Thursday in class, and then we will also be reviewing for your next test.